In the second part about detectors, I'll be talking exclusively about cameras, and we'll now be talking about their specifications and their performance. So basically this will be very useful if you decide to buy a camera. What are you going to pay attention to? But also when you already have a camera, it is highly useful to understand how it works and when your camera is actually limiting your signal-noise ratio, i.e. the quality of your experiments, or when there's something else going on. So camera specifications are often and always should be provided by the manufacturer. And so I pulled down here the specifications for one of these scientific grade cameras, not an endorsement for this specific one at all, but just to have an example. And so at the end of the talk, we'll basically have gone through everything that we see here on this spec sheet. Also, as you will see, there are two basic types of chips that are being used at the moment in scientific imaging. And one is the so-called interline chip, as we discussed in the first detector lecture. There's like a classic Sony chip, the ICX285, that you will see in many, many cameras. The other is this frame transfer chip that has EM gain, and I'll explain that in a little bit. And this is a chip made by E2V, the CCD97, that is in many cameras that we like a lot. So first of all, pixel size and number. So of course, you know, you want a lot of pixels, and in the end you also want them to be a certain size, but what is the right size for your microscope system? Now this Sony Interline ICX285, and although this particular camera says it's not one of those, its specs are highly, highly similar, has 1040 by 1392 photosensitive elements, pixels, and they are each 6.45 microns on a side, so 6.45 microns square. So is that good or is that bad? So one thing to keep in mind is when you project an image through your lens onto the camera, there's often no additional magnification there, and so that means that you can now back calculate what a 6.45 micron pixel corresponds to in your sample plane. So if you have a 100x objective, that means that you have 65 nanometers, 6.45 microns divided by 100, 65 nanometers per pixel. So is that okay? Now, what we all kind of intuitively know is that if you have a lot of pixels, if you have few pixels, that the image looks very blocky, and that is bad. And the more pixels you get, the less blockier and the better looking it becomes. But is there some kind of limit to this? Should we just be throwing more and more smaller and smaller pixels at it, or is there a certain optimum? Well, the answer to that comes from very old sampling theorem. And so the question is, how many pixels do we need to reproduce the smallest thing that we can discriminate in our microscope? And this Nyquist-Shannon sampling theorem that actually came out of old signal processing work on much more linear signals. But it states that to sample an analog signal, you need at least 2 pixels per resolvable element. So what we tend to tell people is that we really like a little bit more than that, so between 2 and 3 pixels. And that way, there's a very intuitive way of thinking about it, and that is if we have 2 points that are just resolvable within our microscope, if we then digitally sample those 2 points, we will need at least 3 pixels to see them. So to have like 1 pixel, 2 bright pixels to represent the points themselves, and then one in between so that we can actually see that there's a dip and that these two things are separated. So 2 to 3 pixels per resolvable element is what we want. So that then brings us to a resolution-centric view of pixel size and how to match your pixel size to your camera. So the first thing that we want to know is what is the actual resolution of the microscope itself. And so, as you have learned in other lectures, that resolution is a function of the numerical aperture of the objective, and it's a function of the wavelength of the light. And so, if you have a objective that has a numerical aperture of 1.4, so a nice oil immersion lens, and you have green light, you're imaging GFP or something, that gives you a resolution of roughly 220 nanometers. Now, if you want 2 pixels per 220 nanometers, as the Nyquist-Shannon theorem states, that means that you need 110 nanometers per pixel. So, instead of choosing a camera with a different pixel size, you can now choose an objective that has a certain magnification so that you end up with 110 nanometers per pixel. So we can simply calculate that for these 6.5 micron pixels, so we need 110 nanometer in the end, and that means that we need a magnification of 58.6, or roughly a 60x magnification. So therefore, a 60x lens would be fine with this. A 40x lens, we would be undersampling. We would be looking at a larger field of view, but we would not be getting the full resolution out of it. And a 100x lens would be oversampling. But also note that the 100x lens would give you about 3 pixels per resolvable element. And we said previously we kind of like that too. So this 6.5 micron square pixels really matches our 60 and 100x oil immersion lenses very well. And that is one of the reasons why this particular chip has become so popular in microscopy. Another important aspect of cameras is how well they transform incoming photons into charge that then can be measured out. And that is called the quantum efficiency. So a maximum quantum efficiency would be 100%. Every photon in is being transferred into an electron that we then can measure. You see here 2 curves. One looks pretty good, goes up to 70% or so. The other one looks less good, goes up to 40% or so. Both of these are not as good as what we get in real life. We can get for front-illuminated CCDs something up to 70% in the green. And for these back-illuminated CCDs, we can actually go up to 95% or so. So pretty amazing. Almost every photon that hits it will be detected. So what is the difference now between this back-illuminated and front-illuminated? Well, front-illuminated means that we come from the top of that chip, we go through these transparent electrons, all the other stuff that the chip manufacturer needed to put there to make the chip actually work. All of that absorbs a tiny little bit of the light, and that reduces the quantum efficiency. So the trick in a back-illuminated CCD is to put the chip upside down and now to carve out that backing of the chip so that the photons hit immediately the photosensitive material. So you can already see that, intuitively understand that to do that backing and making that chip very, very thin, that's a very difficult process, and that a lot of them will actually break or get lost in the process. And so that makes these back-thin CCDs substantially more expensive than front-illuminated ones, but they bring us that higher quantum efficiency that we very much like. Okay, I'll now talk about different types of noise, because in the end what we care about is our signal over noise. So understanding noise is important in in making that ratio, the signal-noise ratio, as good as possible. So we all intuitively understand that when you decrease your exposure time, your image gets grainier and grainier, worse and worse. So you get more and more noise and less signal. So, but why is that really the case? Why does your signal-noise ratio decrease with decreasing exposure time? There are 4 major types of noise that are important to understanding our cameras. And the very first one is the most fundamental one, and that is this photon shot noise. And basically, this is due to the fact that light is not only a wave, but also a particle. And so to measure light, you have to imagine that there's this continuous bombardment happening with particles. And if you do a measurement during a given time period, that measurement is never going to be exact for the rate with which these photons hit you. So, and that is simply given by nature, that there's no continuous stream of photons. Photons arrive with a certain irregularity, and that's what we call photon shot noise. So it's given by nature, our camera cannot help it. All we know is that it scales with the square root of the number of photons. So already here you see, if I get more photons, since this only goes with the square root, I'll improve my signal-noise ratio. Then another important type of noise, and this is coming from our camera, is the read noise. So remember in that first lecture we had a little measuring cup that was measuring out how much water was in these buckets. Well, here in the CCD we're also measuring, and there's simply an error in measuring how much charge is in each of these pixels. And you can also understand that the faster you start to read out, the larger that error becomes. So this error is independent of the number of photons hitting the chip. It's for every pixel there's a certain error added on by our CCD camera. And so this is a number that you can measure, and our camera manufacturer will tell us, and you will see here that we have it gives us the read noise in electrons, photoelectrons, and it also tells us that at a lower speed we have a lower read noise than at a higher speed. So this is a property of the camera and the speed with which you read out the camera. Another type of noise that we often don't think about too much is fixed pattern noise. So if we illuminate the chip with a very homogeneous light that illuminates everything evenly, you will see that not all the pixels in that chip respond exactly the same. Some of them will be a bit dimmer, others will be a bit brighter. There will be patterns, depending on how the chip was manufactured. So this fixed pattern noise scales linearly with the signal. And what you also can do is you can take a control image, a flat field image, where you do this illumination of the whole chip in one go, and then use that to correct the image that you measure so that you take out this fixed pattern noise. Another type of noise is dark current. So the chip, even when there's no light hitting it, will accumulate a tiny little bit of charge. And the longer you expose, and also the warmer the camera itself is, the more of that charge will show up. So by cooling the camera, the manufacturers reduce this dark current dramatically. And you will see here that for this specific chip, we have a dark current of something like 0.00005 electrons per second. And that means you would need to expose 2,000 seconds before, on average, you get 1 electron dark current per pixel. And so in practice, our exposure times are way lower, and that means that in normal use, this dark current is not really an issue. So that leaves us the two main important noise sources, the photon shot noise and the readout noise. Now if we put that semi-mathematically, so what we are interested in is measuring the signal-noise ratio. So we know that our signal scales with the number of photons. So for the noise, we have a contribution of the read noise, and we have a contribution of the photon shot noise, square root of the number of photons. And we can express that then as the square root of the read noise squared plus the number of photons. And from this simple equation, you can see that they're basically two different regimens. So when we have a lot of light, or enough light so that we get out of that read noise squared, when we're higher than the read noise squared, then we're shot noise limited. Whereas when the number of photons is smaller than the read noise squared, then we're limited by our read noise. And those are two different regimens, because in this case we really care about the camera, whereas here we really don't. Now this also, once you have a shot noise limited image, so the camera is really fine, it's just nature that limits our noise. So what can you do to improve the signal-noise ratio? Well, you have to, if you want to double your signal-noise ratio, you'll need to increase your number of photons 4 times, so that square root of 4 is 2, so that you double the signal-noise ratio. So you can do that by exposing 4 times as long, and this is why longer exposures look better. Alternative strategy is to use 2x2 binning. So what is binning? Well, in binning, we are now reading out multiple pixels at the same time. So we're using these pixel shifting technology of the CCD to shift twice into this serial readout register, so that you accumulate the charge of these 2 pixels into this one here. And then in that serial readout register, we do the same trick again. We shift twice into the readout amplifier, so that in the end the readout amplifier now has a charge of these 4 pixels here and reads that out in one go. And that means that we now have the charge of 4 pixels, we have only 1 readout noise contribution. So we increase the signal-noise ratio by doing this twofold. And of course, we also are faster, because this all takes, since the readout takes most of the time, this means that we lower the total readout time by 2 or 4-fold. But of course, we're giving up spatial resolution. So we now have, like, instead of a 6.5 micron pixel, we have kind of a 13 micron virtual pixel. Okay, so back to readout noise and photon shot noise. Now, so what we saw is that when the photon rate is somewhere on the order of the square of the readout noise, that is where the readout noise becomes important. And regretfully, since we don't want to use much light in our microscopes, and we don't want to kill our live samples, sometimes we just don't have much light coming out of it, we are often working in this regimen where we're limited by readout noise. So this example shows a sample that has on average a photon flux of 10 photons per pixel. Now, when we add to that the photon shot noise, you already see that the image becomes a lot grainier. But on the other hand, this is the best that you can do in nature. This is just a simulation. This would be the real image that you get. Now, if we have a camera with 5 electrons read noise, and that is actually pretty good, it becomes more or less unusable. So what you should remember here is that, so we have here 10 photons per pixel on average. Square root of 10 is roughly 3. So we have here the photon shot noise is like about 60% of the readout noise, and that is really, an area that you don't want to be. So what you like to do is to reduce the readout noise of the camera. Now there are multiple technologies that accomplish that to an extent. And one of them that has become really popular is this electron multiplication process. So what happens here is that we amplify the signal on the chip before it goes to the readout amplifier. So these chips have a special register. They have a special electron multiplication register. And in that register, the charge is being clocked into the next well with a very high voltage, much higher than normal. And just as in this avalanche photodiode that I talked about in the first lecture, we now get an amplification of the number of electrons. So on average, with every pixel that you move, you get like, depending on the voltage you put over them, you get like just up to 2% more electrons. But if you now do this 512 times, you get really an enormous amplification of the signal. So now what the net effect is here is that we amplify these one or a few electrons before it goes to the amplifier. So the amplifier sees like, let's say, 100 to 1,000 electrons and then adds it readout noise. But since the signal is now much higher than the readout noise, we don't really care anymore. So to summarize, these EM CCDs have a fast, relatively noisy CCD. So they can often, the chip at these fast speeds can have pretty high read noise itself. But since we amplify the signal by, for instance, 100-fold, that 50 electron read noise now looks like half an electron. Well, that's great. So the downside of this is that that amplification process itself is also stochastic. When we go from one well to the other, where we have the high voltage and impact ionization, that is a stochastic process as well. And that kind of looks the same as that Poisson shot noise. And so some people think about EM gain as if you are halving the quantum efficiency of your chip. The real good thing is that you get your image really fast and you don't have to worry about readout noise anymore. Now, this used to be the major game in town for a couple of years, but very recently the camera manufacturers realized that they could actually use the CMOS architecture. So this is the photoelectric cells that have a few transistors built around them. So and they transfer the charge into a voltage right there at the pixel. These things can run very, very fast, and it so turned out that they can actually make them such that they have very low read noise. So the scientific CMOS cameras claim, some of them claim to have a read noise that is less than 1.5 electrons, and that is really in a very nice area where this basically becomes so low that you don't care about it. So the current architectures look like these cameras have often something like 2,000 by 2,000 pixels at 6.5 microns. So it's huge. It's really like 3 to 4 times larger than that interline chip that I've been talking about. They also can run extremely fast. So they out of the box can go 100 frames per second at full chip. And you can even take subregions of those cameras up to like 25,000 frames per second. So that opens up a whole new realm of imaging. They do have quite a bit of fixed pattern noise, but that's something you can deal with. These cameras tend to have a lot of logic on board, so that a lot of these corrections are already being taken care of inside the camera. And one thing to remember is when you use a CMOS camera, since you now have the analog to voltage conversion right at the chip, at the pixel itself, so binning does not, as in a CCD, reduce the readout noise, because each of these pixels causes its own readout noise. Now, another interesting feature of these CMOS cameras is that they don't read out the whole chip in one go. the readout, the start of the exposure and the readout often goes in kind of a wave. And this is called a rolling shutter. Some of them also can operate in this global shutter mode where you expose in one go, but then they have a higher readout noise again. But this reading out in a wave this rolling shutter is something you need to be aware of. Since our specimens often don't move very fast, it's not like a big issue. But the following image that was taken from a propeller plane that was taken with a camera that has this rolling shutter, you can see that there are beautiful artifacts happening because we're now exposing the camera not in one go, so that you get kind of very weird looking pictures. So be aware of that rolling shutter issue. Another specification of the camera is its dynamic range, and that is how many different intensity levels can it discriminate. Well, that depends on the full well capacity, so how much charge can I pack into a well before it starts overflowing. And it also depends on what is the smallest step that I can discriminate. Well, the full well capacity is something you or the manufacturer can measure. And the smallest step is given by the readout noise. And that means that we can simply divide the full well capacity by the readout noise, and that gives us the dynamic range. This is a little bit an optimistic measure. What might be a little bit better is something like 90% of the full well capacity. And then we also, our steps, if we say like 3 times the readout noise, that's a lot more conservative. And that still would give us about 1,000 different gray levels that we can really reliably discriminate from each other. Well, our computer screens cannot display more than 256 different grayscale levels. And in part that is because our human eyes really, once they're accommodated to a certain light intensity, really cannot discriminate more than about 100 or so different intensities. So this number was also given on our data sheet. We can see here that we had a full well capacity of something like 18,000 electrons. Then with a 6 electron readout noise, that gave us a dynamic range of 3,000. So the manufacturer used this calculation here where it divided full well capacity straight by the readout noise. That also leads us in another important factor, and that is this so-called bit depth. And this comes more from our computer, because our computer likes to work in bytes that consist of 8 bits. So our camera now has 3,000 different grayscale levels. Well, how is it going to send that to our computer? If it would pack that in 1 byte, 1 bit, then it would be a lost cause, because that you can only stick 256 grayscale levels in that. So you would lose a lot of information. So that means that our camera should be using at least 12 bits or 4,096 grayscale levels to maintain all that information. So you really want to be sure that your camera is spitting out enough bits per pixel to the computer to really reflect the full dynamic range that it can provide you. And so this is also often listed by the manufacturer. So we see that this camera has 2 different modes, and in one of them it can give you 16 bits or 65,000 or so different grayscale levels, which then, by the way, are kind of oversampled because we saw that it cannot discriminate more than 3,000 different intensity levels. One important thing to remember is that that number that you get in the computer does not directly relate to the number of photons hitting that pixel. And that is what you, in the end, really want to know. So first of all, when there are no photons hitting the chip, you do not get the number 0 in your computer. And that is because we have this readout noise, and so if you would now clip all that, you would really be clipping information and there would be information missing. So the manufacturers often set a certain offset, something like 100 or whatever. And in some cameras you can actually change that offset yourself in the software. Always when there's like 0 pixel values, it's highly suspicious that something weird is going on, and don't trust those measurements. Also, an increase by 1 does not mean that there was 1 more photon hitting the pixel. So the so-called electron conversion factor, that is the factor that relates these digital numbers in the computer to the number of photons that hit the pixel. It depends on certain parameters. For instance, it will depend on that electron multiplication gain that we talked about earlier, or also when the camera has an analog gain in its analog to voltage converter, it will change depending on the setting of that gain as well. Now, that photon shot noise that we talked about before happens to give you an amazing way to measuring what that electron conversion factor is. And this is also how the manufacturers themselves measure this. So basically we saw that photon shot noise goes with the square root of the number of the photoelectrons on the camera. The photon conversion, electron conversion factor, photoelectron conversion factor itself is given by the number of photons times this factor times the digital number that we measure from this pixel. Now, likewise, the noise in this also goes with the electron conversion factor. And when we solve those equations for each other, you'll see that the electron conversion factor can be calculated by dividing the digital number of a given measurement by the variance, the square of the noise at that given pixel. And so this equation is valid when we are limited only by photon shot noise. So if we can set up an experiment where we are purely photon shot noise limited, we can, by measuring intensity and by measuring the noise, standard deviation, we can backtrack the electron conversion factor. So in general, measurement of signal versus noise is extremely useful. We call these photon transfer curves. And so you see here kind of a very archetypical photon transfer curve. So the way this is done, there are 2 different ways. One is that you provide constant illumination, and then at every pixel you take many, many measurements, and you calculate the average pixel value and you calculate the noise on that pixel. Alternatively, if you can really illuminate your chip very homogeneously, you can measure the average over all these different pixels, and you can measure the standard deviation, the noise over all these pixels. You do this at different intensity values, and then you plot on a log-log scale the average versus the noise. So in these plots, what you will see is that at low intensities, that the noise will converge to a certain constant, and that constant is of course the readout noise, because no light, the only noise you see is the readout noise. Then when we have a very high intensities, we'll get to a regimen where we're overfilling the well, and since they're all clipped, the noise in the measurement will also drop dramatically, and so this point can give you the full well capacity. Then on these linear areas of this curve, where the intensity scales as the square of the noise, this is where we can read out the electron conversion factor. And it's really kind of amazing how simple these kind of measurements are. And I made a couple of scripts that in our micromanager software can do these measurements. And here you see a photon transfer curve that was actually measured on one of our cameras, and that gives directly the electron conversion factor. Okay, this is where I'm going to leave this lecture about camera specifications. I do want to thank Kurt Thorne. He and I worked both on this lecture quite a bit at various points in time. Some illustrations came from the micro.magnet.fsu.edu website, which is a wonderful resource for anything microscopy related. James Pauly's Handbook of Biological Confocal Microscopy has a great chapter about everything you want to know about CCD cameras, and then a little more. And these photon transfer curves, there's a whole book about them by James Jancic, who also has another very good book about CCDs and how CCDs work. Thank you.